Assalamu alaikum. The presentation is talking about the differences between ASD method and LRFD method. As an introduction, the AISC specification provides two acceptable methods for designing structural steel members and their connections. These are LRFD, load and resistance factor design, and the ASD, which stands for the allowable strength design method. The ASD was used before the introduction of the LRFD in the middle of the 80s, and before that, actually in the early of the 70s, LRFD method was used in concrete. Strength limit states and serviceability limit states. These two limit states must be prevented. What are the states of strength limits? Which define the load carrying capacity. It's the excessive yielding, fracture, buckling, fatigue, and gross rigid body motion. Well, the serviceability limit states, which define performance, including deflection, slipping, cracking, vibration, deterioration, and etc. So these limits must be prevented in our design. The unpredictable nature, the inherent uncertainty of both, the magnitude of the loads acting on a structure, and the ability of the structure to carry those loads. Usually, the effects of multiple loads are additive, but in some cases, for example, a beam column, one load can magnify the effect of another load. So what to do to overcome these uncertainties? In the best of cases, the combined effect of multiple load related to a particular limit state or failure mode can be described with a mathematical probability density function. In addition, the structural limit state can be described by another mathematical probability density function. For this ideal case, the two probability density functions yield a mathematical relation for either the difference between or the ratio of the two means and the possibility that the load will exceed the resistance. Then, based on this, the LRFD method are developed. The margin established between resistance and load in real cases is intended to reduce the probability of failure depending on the consequences of failure or unserviceability. LRFD versus ASD. There are two major differences between LRFD and the ASD. The first pertains to the method used for calculating the design loads. The second difference pertains to the use of resistance factor phi in LRFD and safety factor omega in ASD. A safety factor omega, it's a number usually greater than 1 used in ASD method. The nominal strength of a given limit state is divided by omega and the result compared with the applicable service load condition. On the other hand, we have the resistance factor, which is a number usually less than 1 used in the LRFD method, of course. The nominal strength for a given limit state multiplied by phi and the result compared with the applicable factored load condition. Now let's move on to the computations for the LRFD. With the LRFD method, possible service load groups are formed and each service load is multiplied by a load factor, which is normally larger than 1. So the magnitude of the load factor reflects the uncertainty of that particular load. The resulting linear combination of service loads in a group, each multiplied by its respective load factor, is called a factored load. The largest value determined in this manner are used to compute the moments, shears, and other forces in the structure. These controlling values may not be larger than nominal strength of the members multiplied by the reduction factors Thus, the factor of safety have been incorporated in the load factors, and we can say the reduction factor phi times the nominal strength of the member must be larger or equal to the computed factored force in the member, symbolized as phi times Rn greater than or equal R sub u. What are the load combination for the LRFD? According to the IISC manual, chapter 2, page 10, the load combinations is based on the ASCE SEI Committee 7 in section 2.3 as this. U, which is the ultimate load, either equal to 1.4 times the dead load, or 2, which is 1.2 times the D, which is the dead load, plus 1.6 times L, plus 0.5 times the LR or S or R. These symbols are explained below the notations. U for the ultimate, D for dead, and etc. The first two are the mostly used in steel design. Okay, here in this table, some typical values for phi. As we see that phi for the tension member in the yielding state is 0.9, while in the fracture state 0.75. The difference here is related to our understanding to this phenomena. So the fracture state, it is not well versed or understood well to make the resistance factor higher. So higher the resistance factor, higher the reliability for our design. So, and so on. For the rest, for the compression, for the flexure and shear in the beams, and for the fasteners. Move on to the ASD computations. With the ASD, service load generally not multiplied by load factors or safety factors. Rather, they are summed up as is for various feasible combinations, and the largest value so obtained are used to compute the force in the members. These total forces may not be greater than the nominal strengths of the members, divided by appropriate safety factors. In equation form, the statement may be written as nominal strength of the member, Rn, divided by the safety factor omega greater than or equal to the largest computed force in member Ra. Symbolically, as it is clear, what are the relationship between omega, the safety factor, and phi, or the resistance factor? Generally, the relationship between them, that omega is equal 1.5 divided by phi. If we take an example, the phi equal 0.9, omega will equal 1.67 as we divide 1.5 by 0.9. And similar to the LRFD, the ASD also have a load combination from the AISC specification, also based on the ISCE SEI Committee 7 section 2.4. The load combinations are clear on the screen. Now we have a typical values for omega for tension member in the yielding state, for a fracture state, and so on and so forth. Move on to discuss the factors for uncertainties, where the uncertainties come from. Number one is the material strengths may initially vary appreciably from their assumed values, and they will vary more with the time due to creep, corrosion, and fatigues. Number two is the methods of analysis are often subject to considerable error. Number three, the so-called acts of God, like hurricanes, earthquakes, floods, etc. These conditions are difficult to predict. Number four, the stresses produced during fabrication and erection are often severe. Laborers in shop and field seem to treat steel shapes with reckless abandon. They drop them, they ram them, they force the members into position to line up the bolt holes. In fact, the stresses during fabrication and erection may exceed those that occur after the structure is completed. Number five, there are technological changes that affect the magnitude of live loads the constantly increasing traffic loads applied to the bridges through the years is one illustration. Like the wind also seems to blow harder as the years go by, or at least building codes keep rising the minimum design wind pressure as more is learned about the subject. Number 6, although the dead loads of a structure can usually be estimated quite closely, the estimation of live loads is more inaccurate. This is particularly true to estimate the worst condition or the worst combination of live loads occurring at any one time. So our conclusion, the LRFD and ASD are both used in the design procedure simultaneously, and it returns to the designer to decide which approach he takes based on some factors like economic and so on. The LRFD is sometimes more economical because of the smaller dead load factors and the LRFD design compared with the load factors used for live loads. So that gives the LRFD maybe a little or a small advantage. Here's some references I used in this presentation. You can go search them and find more about this subject. Finally, thanks for your attention.